Okay, so welcome to my video on squeeze theorem. I think this is a very important notion, very important for Cal 1. We use it a lot in Cal 2 as well. What squeeze theorem says, I'm not going to prove it in this video, but I'll just show you the idea and a bit of applications, some examples. So it states that if f of x is smaller or equal to g of x, which is smaller or equal to h of x, when x approaches some value a, and the limit of f of x as x approaches a and the limit of h of x as x approaches a is equal to some limit, then g of x, which is in between the two values, f and h, also goes to that same limit. So let's draw a sketch just to have an idea of what's going on. So essentially, we have x and y. We have some function, f is the smaller one, so let's call f something like this. This is f. And then we have h of x, which is larger, so something like this. This is our h of x. And it's tending towards essentially the same value at a, so the limit is almost the same at a. And we have g of x, which is in between f of x and h of x. So g of x is somewhere here in between, just squiggling in between. And he levels out in between. So in red, this is our g of x. So essentially it's called the squeeze theorem or the sandwich theorem because h and f are squeezing g of x, forcing it to go to the same limit as them as x approaches a. So g of x is forced to go to the same limit. Okay, so this is the idea of squeeze theorem. Okay, so g of x stuck in between f of x and h of x tends to the same limit as h of x and f of x. What's larger and what's smaller. Okay, so let's take a look at an example. Okay, so in this example here for squeeze theorem, it's asking us to evaluate, specifically to use squeeze theorem to find the limit as x approaches 7 of f of x. And they tell us that f of x is bounded between 3x minus 1, so it has to be bigger than 3x minus 1, but at the same time it's smaller or equal to x squared minus 29. Okay, so we don't know anything about the function f of x. All we know is that it's bounded between these two values. Okay, and we want to know the limit as x approaches 7 of f of x. So essentially what we're doing is we're going to apply squeeze theorem. We're going to take the limit as x approaches 7 of the outer bounds. And hopefully if this gives us the same value, that's going to give us information of f of x, which is bounded in between. So even though we don't know what this function is, we could actually still evaluate it using the squeeze theorem argument. So taking here the limit as x approaches 7, what you're doing is you're substituting x with 7, direct substitution. So 3 times 7 minus 1, 21 minus 1 is 20, less than or equal to f of x, which is less than or equal to, and here we're going to take the limit as well, as x approaches 7. So 7 squared is 49, 49 minus 29 also gives us 20. So f of x has to be between, sorry, I shouldn't write f of x, we're taking the limit. The limit as x approaches 7 of f of x, we took the limit on all three sides, is bounded between 20 and 20. Therefore, by squeeze theorem, the limit of as x approaches 7 of f of x is equal to 20. So it's important when you're using a squeeze theorem argument to state that you're using squeeze theorem. So therefore, the limit as x approaches 7 of f of x equals 20 by squeeze theorem. Good. Let's take a look at another example. Okay, so in this example here for squeeze theorem, it's asking us to show that the limit as x tends to 0 of x to the 2022 times cos of everything in this bracket, pi times e to the log of 14 divided by x to the math times x to the is times x to the fun, assuming all these are constants, show that this limit here is equal to 0. Okay. So this is a very typical squeeze theorem problem. We start off with, so let's do the solution. We begin with the fact that cosine of x, so typically you're given a cos or a sine, and we start off with the fact that cos of x is bounded, is stuck in between. So consider the cos function. Cos starts at 1, or think of the unit circle as well, that's fine. but cos oscillates between -1 and 1. And it continues this pattern to the right and to the left forever. This is cos. Sine does the same thing, but starts at the origin and follows a similar pattern. But essentially cos and sine are both stuck in between -1 and 1. So cos of x is bounded below by -1 and bounded above by +1. This is always the argument that we start off with. Okay. So we know that to be true. And what we're going to do is we're going to build towards what we have here. So the next step is to put whatever we have in the bracket or in the argument of the cos here. Well, think of the unit circle. The argument or the angle, does that change by moving the angle? Does that change the radius of the circle? No, because you're essentially just turning. The angle is just turning inside the unit circle, whereas the radius remains 1. So all this here, my teacher used to call this a shadow. It's just there to scare you. Don't let this bother you, because this doesn't really affect the fact that cos is bounded between -1 and 1. In order to change the amplitude or the radius of the circle, you have to multiply cos by some constant a, and that's going to affect what it's bounded by. But in this case here, whatever's inside the argument, inside the cos, does not affect what it's bounded by. So we could state that -1, so cos of everything that's in the bracket, doesn't matter what's in there, pi e to the log 14, all that divided by x to the math is fun. It's still going to be bounded between -1 and 1. So this is great. So we're almost there. We're almost done building towards this whole thing. The next piece that we have to deal with is the multiplication of x to the 2022. So x to the 2022, since the exponent is it's an even value, the exponent's even, which means the whole number here is positive. So we're going to just multiply all three sides by x to the 2022. And notice that we're working with inequalities, so since this cannot be negative, we don't have to worry about switching the signs. So we're essentially just going to multiply the left hand side by x to the 2022, the middle by x to the 2022, cos pi e to the log 14, x math is fun, and x to the 2022. Okay, so to deal with everything in the middle, we're not able to. We're not able to evaluate this limit because substituting x with 0 into here right off the bat, in the beginning you're going to get 0, because 0 to the 2022 is still 0, times cos of, you have a number divided by 0, because you're replacing the x here onto the denominator by 0. So we are not able to divide by 0, or we're not able to evaluate this. So direct substitution in this case should have been our first attempt, but it doesn't work. So we're forced to use a squeeze theorem argument. Next step that we do is evaluating this limit doesn't work for us, so what we're going to do is evaluate the ends. So if we look at the ends and take the limit of the endpoint as x goes to 0, well, this is easy to evaluate. The limit as x goes to 0 of negative x to the 2022 is just 0. And then this whole thing here, we're just going to replace it in here. And over here, again, we're going to take the limit as x approaches 0. And taking the limit as x goes to 0 of x to the 2022, again, it's just 0. So what we showed here is that whatever's in the middle has to be bigger or equal to 0, but at the same time has to be smaller or equal to 0. The only way for that to be possible is that it's equal to 0. Therefore, the limit as x approaches 0 of x to the 2022 of cos pi e log 14 over x, math is fun, has to be equal to 0 by Squeeze theorem. In order to use Squeeze theorem, these two values have to be the same. They don't necessarily have to be 0, but they have to be the same number. Okay. And we're done. So this is a typical Squeeze theorem problem. Let's look at another example. Okay, so in this example here, they're asking us to use Squeeze theorem to evaluate this limit as x approaches 0, x to the 4 times sine squared of 2 pi over x. So the first thing we do is we begin by arguing that sine is bounded in between. So this is our solution. We argue that sine of x is bounded in between -1 and 1. We know this because our sine function oscillates between -1 and 1 forever. 1 and -1. This is what our sine function looks like. So this you should know. So we're just using the fact that it's bounded between -1 and 1 if you don't believe me. Or you could also use the argument of the unit circle. So if we're looking at our unit circle, our y's values, the highest value is 1, the lowest value is -1, because sine is read on the y. Same for cos. Cos is read on the x, so it goes from -1 to 1. Those are the extreme values. So we start off with that, but we don't have sine. In this case here, this is notation that we use. We write sine squared. Sine squared, you should be thinking of it as sine of 2 pi over x. Think of it as all that squared. Okay. So this and this is the same. It means the exact same thing. But for notation, not to get confused, we don't put the exponent 2 inside the bracket. It's specifically on the sine. That's why we write it here. So what do we know about sine squared? Well, sine squared, you can't have any negative values. So if you're thinking of squaring all three sides, you're going to get something like this, which is a false argument. You're saying sine is in between 1 and 1. Not necessarily true. Sine squared, if you graph it, it looks something like this. But essentially all the negative sides, because you can't have any negative values, bounce up. So this is what a sine squared function would look like. Oops, sorry. Something like this. So you can't have any negative values because it's squared. But the lowest value is not necessarily 1. The lowest value that you get is 0. So typical argument, sine is bounded between -1 and 1. If we square it, then the argument is between 0 and 1. Okay. So sine squared is between 0 and 1. So we're slowly building towards what we have here. The next step that we're missing is what's inside the sine, the angle. And again, same reasoning as we saw in a previous example. Whatever's inside the angle of sine doesn't change the radius or its length. So this is still going to remain within these same boundaries. So 2 pi over x. Essentially, sine squared of anything is between 0 and 1. So this is just there to scare you. And lastly, what we need is the x to the 4. So x to the 4 is positive because the exponent's even. So we don't have to worry about switching the signs on the inequalities. So we're going to just multiply all three sides by x to the 4. So this times x to the 4, this times x to the 4, and this times x to the 4. Giving us 0 less than or equal to x to the 4 sine squared of 2 pi over x. And then which is less than 1 times x to the 4, which is x to the 4. And now we're just going to take the limit as x goes to 0 on all three sides. So here if we take the limit as x goes to 0, this is the constant property. There's no x's in here, so it just remains as 0. Less than the limit as x goes to 0 of this whole thing, which we cannot evaluate. Direct substitution doesn't work in this case because we're dividing by x. So we get a number divided by 0, which we don't know how to deal with. In advanced calculus or in analysis, you will be able to do this. There's a different theorem that you could use, but I won't speak about this now because you don't usually see this in college. And lastly, we have the limit as x goes to 0 of x to the 4. So we're replacing our x with 0, 0 to the 4 is still 0. So we got this thing in the middle here is bounded below by 0, but bounded also above by 0. So the only way for it to be bounded above and below by 0 is that if it's equal to 0. by Squeeze theorem. So by Squeeze theorem, this thing here has to be equal to 0, and we're done. Okay, so I hope this helped, and I hope you enjoy my videos on Squeeze theorem. I'll see you in the next video.